Hello, dear learners. Welcome back to Lesson BC YouTube channel. Today, we will see Introduction to Magnetism. Don't forget to subscribe and like our channel.
Okay, let's dive right in. We're talking about magnetism, one of those fundamental forces of nature. And usually you can't see it, right? But what you're looking at here is pretty amazing. We've made the invisible visible. These little bits of iron are tracing out the unseen patterns of a magnetic field, showing us its awesome and powerful structure. So how does all this work? Well, that's what we're here to find out.
So, here's our game plan for today. We'll start with the absolute basics. What even is a magnet? Then, we'll figure out how to see its invisible field and discover how our entire planet acts like one giant magnet. After that, and this is super cool, we'll uncover the secret link between magnetism and electricity, learn a handy trick called the right-hand rule, and finally, we'll even do some math to calculate a magnetic field's strength. Let's jump in. First things first, what exactly makes a magnet a magnet? Let's break down the most fundamental properties of these amazing objects.
Every magnet, and I mean every single one, has two ends, a North Pole and a South Pole. And the number one rule you absolutely have to know is really simple. Opposites attract and likes repel. So if you try to push two North Poles together, you'll feel them push each other apart. Same thing happens with two South Poles. But bring a North and a South Pole close, and snap. They'll pull together with an attractive force.
So what can a magnet actually stick to? You might be surprised to learn it's not every type of metal. Only certain materials like iron, nickel, and cobalt are strongly attracted to magnets. The special name for these is ferromagnetic materials. And what's really neat is that these are the same materials that can be turned into permanent magnets themselves.
Now, a magnet's force isn't just right at its surface. Nope, it actually extends out into the space all around it. We call this area of influence the magnetic field, and we've got a pretty clever way to see it.
We use these imaginary lines called, you guessed it, magnetic field lines, to draw a map of this invisible field. And by agreement, scientists decided that these lines always flow out of the North Pole and loop around into the South Pole. They create this complete, continuous circuit of force.
And this is where it gets really interesting. Look how these lines show us exactly what's happening between two different magnets. On the left, with the North and South Pole facing each other, you see the lines actually connect, bridging the gap between them. That's attraction. But on the right, between two North Poles, the lines bend and push away from each other. That's a perfect picture of repulsion.
Okay, so let's lock in the three key rules for these field lines. You'll definitely want to remember these. Rule 1, they always travel from north to south. Rule 2, they can never, ever cross each other. And Rule 3, the closer together the lines are, the stronger the magnetic field is in that area. That's why they're so bunched up near the poles. Now let's take everything we've just learned and scale it up, like way, way up. Because believe it or not, you're standing on a giant magnet right this very second.
Yup, it's true. Our planet Earth acts just like a massive bar magnet. All that swirling molten iron deep in the Earth's core generates a gigantic magnetic field that surrounds the entire globe. And that is exactly why a compass works. The tiny magnet in a compass needle just lines itself up with the Earth's magnetic field lines, and that's why it always points north.
And our planet's magnetic field does one of the most important jobs imaginable. It acts like a giant invisible shield, protecting us from a constant stream of nasty, high-energy particles flying off the sun. We call that the solar wind. When those particles get caught in our magnetic field and funneled toward the poles, they crash into our atmosphere and create that absolutely breathtaking light show we call the aurora.
So we've seen magnetism in refrigerator magnets and in the very core of the Earth. So you might be thinking, okay, I get it, magnetism is just a thing that special rocks and planets have. But what if I told you there was a deeper secret, a hidden connection?
That's right, magnetism isn't just about magnets. It is fundamentally, deeply tied to electricity. They're actually two sides of the very same coin, a force that we call electromagnetism.
Okay, this is the key idea. So listen close. Anytime you have moving electric charges, like all the electrons flowing through a wire to power your phone, it generates a magnetic field. And this field wraps around the wire in perfect circles. You turn the current on, the magnetic field just appears. You turn it off, and poof, it's gone. And this whole revolutionary idea was discovered completely by accident. Picture this, it's 1820, and a physicist named Hans Christian Ørsted is giving a lecture. He switches on an electric circuit, and he just happens to notice that the needle on a compass sitting nearby suddenly twitches. He was the very first person to see concrete proof that electricity creates magnetism, and it completely changed the world of physics forever.
So we know that a current in a wire creates a magnetic field. But which way does that field wrap around? Does it go clockwise? Counterclockwise? How can we figure that out? Well, luckily for us, there's a really simple trick. It's called the right hand grip rule. And you can do this right now. Take your right hand, point your thumb in the direction the current is flowing. Now curl your fingers around, like you're grabbing the wire. The direction that your fingers are pointing, that's the direction of the magnetic field. Simple as that.
Just take a look at the diagram here. The thumb is pointing up, following the arrow for the current, which we label I. And you can clearly see how the fingers curl around in a counterclockwise circle. That's the direction of the magnetic field, which we call B. It's a super useful trick to remember this key physics concept.
Okay, so we've got the direction figured out, but this is physics. We love numbers. How strong is that field? Knowing the strength is absolutely crucial for building things like electric motors or even hospital MRI machines. So of course, we've got an equation for that.
All right, don't let all the symbols intimidate you. This is the formula for the magnetic field strength B around a long straight wire. Let's break it down. B is what we're looking for, the field strength, and we measure it in a unit called Teslas. I is just the current in the wire, and R is how far away you are from the wire. That symbol, μ0, is just a special number in physics, a constant of nature. The big takeaway here? The field gets stronger if you have more current or if you get closer to the wire.
Okay, let's actually use this formula. Let's say we have a wire with 5 amps of current, and we want to know the field strength 0.02 meters away from it. Step 1, we write down our formula. Step 2, we just plug in the numbers we know. Now notice how there's a 4 pi on top and a 2 pi on the bottom? They simplify really nicely, which makes our math easier. We do the multiplication and division, and we get our final answer. 5 times 10 to the negative 5 Tesla. Not so bad, right?
All right, time for a quick pop quiz to see what you've learned. First question. What happens when you bring a magnet's south pole near another magnet's north pole? Second, in which direction do magnetic field lines travel outside a magnet? And last one, if you flip the direction of the current in a wire, what happens to the magnetic field? Think about that right-hand rule we just learned. Excellent work today, everyone. We've gone from the simple push and pull of magnets all the way to the huge magnetic field that protects our entire world. Physics is all about finding these hidden rules that run the universe. So the next time you use a compass, just remember the incredible science that's making it work. Keep asking questions, stay curious, and we'll see you in the next lesson.